So kurtosis is one of the most misunderstood concepts in statistics. Some say it measures pickedness, some say outliers, but neither explanation feels fully satisfying. So in this video, let's understand what kurtosis actually signifies. For your information, kurtosis is introduced by Carl Pearson in 1905. Now, see, kurtosis is a measure to describe a numerical dataset. Okay, now the curve that you are seeing on this screen, the bell curve, this represents the data distribution curve of a numerical dataset, where x-axis represents the data points and y-axis represents the probability density. In simple words, probability density is at any x value, probability density gives how many data points are concentrated around that x value. So if at an x value probability density is higher, then it means more data points are concentrated around that x value. And if at any x value probability density is lower, then it means less number of data points are concentrated around that value. Okay, now area between 2 points gives the percentage of total data points in this area. Okay, and area of the curve is 100% or 1, which signifies the entire data set. Okay, now, so kurtosis is a measure to describe a numerical data set. Now what it describes? It describes how data is distributed around the tail, or in other words, it gives a quantitative measure of how many data points are there in the tail and how extreme the data points are from the center. So some of us might think that it is talking about spread of the dataset, but no, because spread means how far the data values are scattered from one another or from the center. So spread is talking in terms of all the data points, whereas kurtosis talks in terms of data points that are only in the tail. Okay. Now for an analogy, just like hotness is an abstract idea, and to measure it, temperature scales are introduced. Now, spread is also an abstract property of a dataset, of a numerical dataset, and to quantify or make this abstract idea measurable, several measures such as interquartile range, variance range are developed, are introduced. Okay. So similarly, tail behavior of a dataset is also abstract, and kurtosis helps us quantify that. Okay. Now, let's see how to find kurtosis. So this is the formula of kurtosis, where n represents the size of the dataset, how many data points are there in the dataset, xi represents each data points, and mu represents the mean of the dataset. Okay. Now, let's take a numerical dataset and let's find out its kurtosis. So its sample size is 5 because there are 5 data points in this dataset. Okay. The mean is 14.2. Okay. Now, so let's draw a table and find out uh, x minus mu whole square and x minus mu to the power 4 of all the data points. So these are the values that we got. Now take the sum of this x minus mu square column and of this column x minus mu to the power 4. Okay, so these two are nothing but this. Cool. Now what is the kurtosis formula? This is the kurtosis formula, and for our data set which is having 5 data points, 5 numerical values, our kurtosis formula will become something like this. Okay, now plug in the values and we will get our kurtosis. Okay, so till now we understood what kurtosis describes, how to calculate kurtosis of a numerical data set. Now if we are given a numerical data set and we found its kurtosis value, then how do we interpret this kurtosis value? How do we interpret this k? Okay, this kurtosis value, where k represents kurtosis. Okay, now so for this there are 3 types of standard distribution are developed based on kurtosis. So the first one is Mesokurtic. Here the data distribution curve looks like a bell curve. It is the standard normal distribution curve. Okay, and its kurtosis value is 3. Okay, now the second one is Leptokurtic. Okay, and it curves looks something like this, and you can see from the curve that outliers are more likely to occur. Why? Because you can see in the curve that the tails are more extreme than this normal distribution curve, than this mesocortic curve. Okay, and its center also often looks sharper and more peaked than normal distribution curve. And here kurtosis value will be greater than 3. Now the third curve is platykurtic. Okay, and the curve here data is more spread out. Okay, and extreme outliers are less frequent, as you can see from by looking at the tail. Okay, and curve appears more flatter and more spread out, and its kurtosis value is less than 3. So we have this. So if for a numerical data set we found kurtosis value, and if its kurtosis value comes greater than 3, then we can say that either there are more data points concentrated in the tails, or the data points or the outliers are at a more extreme value. That means the deviation of the outlier is more as compared to normal distribution. But if for a numerical data set we found a kurtosis value and its kurtosis value comes less than 3, then we can say that less number of data points are concentrated in the tail, that is less number of outliers. Okay, and if for a data value kurtosis value comes equals to 3, then we can say that it will follow the normal distribution curve. Okay, so kurtosis value is influenced by basically two things. First, how many outliers are there in the data set, and the extremity of the outliers, that is the deviation of the outliers from the mean. So if the number of outliers increases, then it will increase the kurtosis value, or if the extremity of the outliers, that is deviation of the outliers from the mean, increases, then it will also increase the kurtosis value. Okay, so this is it for today, and we will meet in the next video. So yeah, thank you.